So it's been a long time. So since the LDBC project started, so I think it's almost 3 years, right?
2 years.
2 years and a half. And as you may understand, in 2 years and a half, a group of maybe 10 people, I don't know the exact number, can do a lot of work, especially for the social network benchmark interactive workload. And in 15 minutes, it's very difficult to get in detail in all the aspects of the interactive workload. So what I will do, and especially for those who have never been in a TUC meeting before, I will try to speak a little of every part, but put more emphasis on those parts that are newer, that maybe have not been introduced in previous events, especially the workload. So the SNB interactive workload, it's a benchmark that models or proposes challenging but interactive queries on top of a social network. It targets linked data technologies. It's thought to be flexible and easy to use, but also we don't want to limit the benchmark to a subset of systems, so we allow it to be used by technologies that support declarative and API-based interfaces. And in such a benchmark, since we are trying to model the operation of a real social network, we do not focus only on a single metric like throughput, but also latency is important, because in a real social network, you do not only have to serve multiple users, but also give a very good user experience. As all the LDBC social network, the LDBC benchmarks, the queries have followed choke point-based design. We have 14 complex read queries, 7 short read queries, and 8 update queries. More on this now. And everything is provided by the benchmark. So both the driver, both the data generator, all the documentation, of course. We are not providing your suite implementations, but so about the data. The data is generated by DataGen. It's a scalable social network data generator. It generates a real social network with following the characteristics one will find in Facebook. It creates a correlated graph. This means that attributes are correlated. For instance, people from a certain country have a larger probability to have certain names. But also, the edges are correlated. So similar people have a higher probability to have an edge or to be friends. This is commonly known as the homophily principle in the social sciences area. DataGen not only generates a person-person friendship graph, but also the activity of these persons. Let's say the posts, the comments on these posts, likes, this kind of stuff. To generate posts, we follow an event-driven approach, so that the volume of activity is not uniform across the time frame. So we can see here that if we compare the posts as if they were generated uniformly, and when we activate the event generation, we see that we observe spikes of volume. This is to reproduce how a real social network activity is, which is driven by real world events such as sports events, elections, this kind of stuff. Also, it is scalable. We can generate a quite large data set, or 1 terabyte data set in less than 2 hours with a very commodity cluster, I would say, of 10 machines, small machines. And it is deterministic, which allows us to have fair comparisons between vendors. So 2 vendors will, at a given scale factor, will have exactly the same data. And we can also, of course, reproduce the results. And it makes it easier to distribute the data sets, because having to download 1 terabyte dataset, it's not always easy, or having servers to host this such datasets. It doesn't mean that we will not provide these datasets in the future. We propose different scale factors. The scale factors are defined based on the size of the dataset in CSV format on disk. Here we see how some statistics of the different scale factors. For instance, for scale factor 1000, which is 1 terabyte of data, we have a graph of 3.6 billion nodes and about 20 million edges. 20 billion edges, sorry. Where else? Yes, DataGen outputs 3 things. The first is the static part of the network in CSV format. This is the part that it's bulk loaded into the network at load time, into the system at load time. The rest is output as updated streams. So these are the queries that the users do that update the database. So new people are inserted, new posts, new forms, new messages. These updated streams can be partitioned into several partitions, so to have higher throughput. This is for the driver. And we also output the substitution parameters. And these substitution parameters are generated in such a way that to reduce the variability in given a query, to reduce the variability of the times to execute that query. About the different queries we have, we propose, as I said, to have 14 complex reads. These are the interactive queries, but still complex queries. They are designed around the choke points. And I give here 2 examples of queries. The first is query 6, which consists of starting from a person and retrieving the tags which are used to identify the topics that person is interested in, and then find other tags that occur together with this tag on posts that were created by their friends. Another type of queries, it's more traversal-like, which is a query 14, which is given 2 queries. We look for the all shortest path between these 2 queries, and then we compute kind of similarity or a score for each path that is based on the similarity between the persons that are in the path. All complex queries in SNB Interactive start from a given person, or have a single or a double starting point in the case of traversal queries, and navigate around this starting point and touch at least 1 or 2 or more types of different entities. We also have what we call short reads. The short reads are to balance the ratio between read queries and update queries, and they are thought to mimic the behavior of a user in a network. So imagine that you are a user, you go to the network. You might perform a complex query, but you can also, or you will also do simple queries to query, for instance, a specific message to see which was the author of that message, or which friends are the friends of some of the persons of the network, these kind of things. And finally, we have the updates, which are these ones. And these are, as I said before, these are created by DataGen in order to preserve the characteristics of the network. So, because we want that over time, as long as we are inserting new data to a network, all the properties of the network, let's say distributions, correlations, etc., are preserved. So now I will talk about the LDBC workload driver. The workload driver is responsible of generating the workload. The workload is a set of operations. Each of them has a start time and a scheduled start time, which is in real time. Here I put data generated. This is only for the case of updates, as we will see now. Also, each query has a type, and each query has a type of parameters. But depending on the query, these parameters will be retrieved from the substitution parameters provided by DataGen, or from the update streams, or from the results of complex queries. So the first type of query we have, as we said before, are updates. In this case, substitution parameters are those that are provided by DataGen. Their scheduled time is the simulation time, so it's the time that DataGen assigned to that entity to the creation of that entity when it generated the data. Also, then we have the complex reads. Complex reads are fed with the parameters generated by DataGen, and their scheduled start times are assigned by the driver as multiples of update queries. We will see this more in detail now with some examples. And then we have two groups of show reads. One are like person-centric, so that there are show reads that are structured around a person. So, for instance, I want to know the information of a person, or I want to know the friend of that person. Or also I want to know the messages of that person. And then we have the message-centric, which is I want to know the forum of that message, which are the replis, which is his creator, and so on and so forth. After each long read, a sequence of short reads is executed. Each sequence tries to model the activity of a given user. At each step, there's a probability of having a new sequence of short reads. This probability decreases as long as the number of steps is increased. And then, well, as I said, yes, and the substitution parameters for these queries, these short reads, are taken from the recent long reads and recent short reads. Once we have once we load the data into Workload driver, the driver creates a workload which is deterministic. So two successive runs of the driver with the same configuration, with the same data set, will generate the same workload. Each operation is assigned a scheduled start time that is trying to that then the driver tries to execute this scheduled start time as close as possible as the time that was scheduled initially. Then for those systems that might be too powerful for a given data set or not enough powerful for executing a given workload, we have introduced what we call the time compression ratio. Given a workload, which is specified in simulation time, we can stretch this workload, shrink this workload, sorry, or stretch it, so to put more or less pressure to the system under test. So for instance, I have a system that can deal with scale factor 10 very easily. I want to test how faster I could be at maximum for that scale factor, so I can shrink this workload to check which are the limits of my system. Also, the number of worker threads is configurable. We can, of course, we have multiple. We can have multiple queries in parallel. And then the driver produces a log where for each operation we have execute operation, we have the operation type, we have the schedule at the start time, but then we have the actual start time that this operation was executed, and how long did it take. And this is used then for auditing if that run was a valid run. And later Moritz will talk more about this auditing process and what we consider a valid run. Finally, we also have we have also added a validation mode into the driver. This validation mode allows the vendors to create validation datasets, but also allows the vendors to, given a validation dataset, to test their own implementations if they are correct or not. It basically creates a stream of operations and their expected results and the parameters of each operations, and it basically executes the driver reproduces this workload, executes the queries, check the parameters, and see if the results are correct. And as LDBC, we provide validation datasets, official validation dataset that has been cross-validated by the different vendors of the consortium. So here, for instance, I put a workload example. This is a scale factor 10, time compression ratio 0.5. These are 1,000 operations. The number of operations is the number of complex queries and the number of update queries. If you sum the numbers of each of the complex and update queries, it is 1,000. And then the number of, as I said before, number of short reads is generated on the fly. The first observation here is that the number of operations per query type is not the same, so it differs, and now we will see why. As it is the number of update operations, because in a real network, adding users, it's not as frequent as creating a message or issuing a like to post. As I said before, the number of complex reads depends on the number of updates. So for instance, if we, for a scale factor 10, the number of instances of query 1, so one instance of query 1 will be issued per each time we observe 26 updates. But these frequencies are different for different queries, because not all the queries have the same cost or are as equally expensive. But also they are different depending on the scale factor, because not all the queries scale in the same way. I could not resist to make the same joke as in Athens, so please do not take pictures of these numbers. These are execution, the average execution times of Sparsity queries, of the queries of complex queries in Sparsity using different scale factors. It is just to show what I was telling you before. As we can see, not all the queries have the same mean time. So there are queries that are much more expensive than others. But also, not all the queries are scaling in the same way. So this is the reason why we do not execute the same amount of queries given an execution, because otherwise we could have one query dominating the whole workload, which is something we want to avoid. So I think I finish here because I'm running out of time, and because I don't have more slides, of course. And now I think Moritz will present his observations on auditing and introduce the auditing rules to make a run valid. So thank you very much, and enjoy the rest of the talk.
I wonder if there are any questions from the audience.
That was very clear.
Yeah. Yes.
Arnau, so you say that the short reads, So the person-centric and document-centric, very short retrievals, that they take parameters from the result of a preceding complex or long read. Is this already implemented like this, or is this a roadmap issue? Yes. Oh, it's implemented. Great.
No, we can run the benchmark.
Yeah.
The benchmark.
Good to hear.
So
Yeah.
it's all good news.